Hello, my name is Molly O'Brien, and today I will be presenting my paper Mapping DNN Embedding Manifolds for Network Generalization Prediction. Network Generalization Prediction is a task that aims to predict how well a trained DNN will perform in a new operating domain. First, a DNN is trained and tested using a labeled dataset, often referred to as the internal dataset. Then NGP predicts how well the DNN will perform on a new external operating dataset. These predictions are made by leveraging unlabeled images from the operating domain or statistics about the operating domain. In our paper, we propose an embedding map for NGP. The intuition behind our embedding map is that we want to identify regions of the DNN embedding space that are associated with a particular outcome. The outcome is selected to indicate success or failure for a given task. For example, in our image classification experiments, we consider true positive, false negative, false positive, and true negative as the outcomes. To fit the embedding map, we start by projecting the internal test samples into the DNN embedding space. Each test sample is labeled with the outcome observed in testing. Then we fit a decision tree to predict the outcome based on the embedding space location of a test sample. A leaf node in our embedding map corresponds to a contiguous region in the embedding space that's associated with a particular outcome. In the illustration on the right, the different colored boxes represent different leaf nodes in our embedding map. Once the embedding map is fit, we can use it to predict the outcomes for unlabeled operating domain images. Each operating domain image is mapped to a leaf node in our embedding map, and the outcomes of the operating domain images are predicted to have the same distribution as the test images from that same leaf node. For example, we would predict that the operating domain images that map to this left green box would be true positive outcomes. We can aggregate these predictions over all of our operating domain samples to predict the overall probability of success or failure. There are a number of NGP methods that have been proposed in the last year. We compare to two of these works. First, the difference of confidence in NGP approach, which uses the change in the average softmax score between the test and operating data to predict the change in your DNN performance. We also compare to the context subspace NGP approach, which identifies how context, often described using metadata, impacts DNN performance, and then predicts how the overall DNN performance will change based on changes in the operating domain context. In our experiments, we investigate NGP performance across 3 image classification tasks: pedestrian classification, melanoma classification, and animal classification. We consider 5 external operating domains and 3 DNN architectures. Overall, our embedding map has the best average NGP performance. If you're interested, please refer to our paper for additional results and visualizations. Thank you so much for your attention.